Hello everyone, and welcome back. Today we're going to continue our exploration of regression analysis and extend the type of model that we're generally working with, which is typically a linear model to start, and increase that order from a degree 1 model up to a degree n polynomial regression model. So let's first off start off by going over the basics associated to linear regression and some of the things that we can sort of look at to determine whether a linear regression model is actually appropriate. So let's assume we have this set of bivariate data plotted here in gray. Obviously, it appears to be increasing. You don't see any periodic behavior. It doesn't look like an x squared curve or anything fancy. So one would generally say that this is appropriate for a linear regression model. And of course, you can assess, for example, normality, homoscedasticity, independence, and linearity of the means if you really want to go that route. But probably one of the fastest ways you can do to analyze the appropriateness is to look at the standardized residuals or just the residual plot for this particular model. So if we look at the residuals associated to our particular x values, with the x values in the horizontal and the residuals of whichever predictor you want to analyze, x1, x2 down to xp, then if you look at the residuals for this model, then they should appear to be randomly scattered, for example, from typically -3 to 3, especially if you're looking, for example, the standardized residuals. So if you try to fit a line of best fit, for example, to the residual plot, you definitely should get a line that's practically equal to the x-axis, right? So therefore, you should not see any correlation between these data points. In particular, the r-squared value definitely should be approximately equal to 0 for the standardized residual plot. But if we take a look at, for example, a data set that definitely should not follow a linear data set or a linear model, for example, let's assume we have something that looks like that, then obviously fitting a line is not going to be appropriate. And you probably want to fit, for example, a quadratic or a cubic or some other fancy model to this data. For example, we may say that, for example, a quadratic model appears to be the best fit for this data, or possibly even a cubic model to fit that particular data set. So for example, this blue curve could be, for example, y is equal to beta 0 plus beta 1x, and this pink model could be the quadratic extension of that model, which would be, for example, y is equal to alpha 0 plus alpha 1x plus alpha 2x squared. And the only reason I'm using alpha instead of beta is because these coefficients beta 0 and beta 1 are usually not going to be the same as, for example, the intercept in the first order term for the associated quadratic model, so I just want to avoid any confusion that could result between these two very different models. So let's start off with the very basic scenario of polynomial regression where we only have one predictor and one response. So for example, you want to see if there is a relationship between, for example, age and happiness, and that relationship could either be linear, quadratic, cubic, quartic, but you believe that it is a polynomial trend between this predictor variable and this response variable. So let's assume that our predictor variable is going to be represented, for example, by x, and let's assume that our response variable is again y. So our general polynomial regression model is going to be of the following form: beta 0 plus beta 1x plus beta 2x squared, that's going to be our quadratic model, and then beta 3x cubed, that's going to be our cubic model, and we can continue this all the way out to, for example, beta p, should be a plus sign, beta p times x to the power of p plus epsilon, where obviously p should be a natural number. So that's our arbitrary simple polynomial regression model. And obviously, we can write this as a linear regression model by simply redefining what our coefficients are. Because obviously, x is just a variable, so we can actually just call that x1. X squared is actually just another variable that happens to depend on x1, so we can actually just call that x2. We can call x cubed x3 and extend this all the way down to xp. So we're going to have an equivalent representation of this model. In particular, y is equal to beta 0 plus beta 1 x1 plus beta 2x2 plus beta 3x3 all the way down to beta p xp plus epsilon. And notice that these coefficients are the same. I've just redefined these predictor variables x1 down to xp into the positive integer powers of x, right? Here, xk is defined to be equal to x to the power of k, and obviously k is a natural number, right? And we already know how to solve this particular model because we can vectorize this in matrix form and write this as, for example, y is equal to x beta plus epsilon, where x is an m by p plus 1 matrix, beta is a p plus 1 by 1 vector, epsilon is an m by 1 vector, and y is our n by 1 vector of response variables. And we already know that, for example, an unbiased estimator for beta would be equal to beta hat, which can be found by x transpose x inverse times x transpose y, as we've already proven for the multiple linear regression case. Okay, so let's see if we can figure out how to build this particular data matrix or design matrix X. So obviously our sample is going to be a bivariate sample because we just have an X value and a Y value. So our set is going to be of the form X comma Y, where obviously K is going to range from 1 to down to n, and that should be xk and yk. So if we just have technically one predictor, then technically we just should have, for example, a column of 1s and a column of x1s in our design matrix X. So if we start by writing that out, just to see what that would look like, that means that our design matrix X is going to be equal to 1, 1, all the way down to 1, and then x1, x2, all the way down to, for example, xn. And then is going to come our x2 predictor variable values, which are just going to be the squares of the linear terms. So this is going to be, for example, x1 squared, x2 squared, all the way down to xn squared, and obviously this is going to extend all the way down to x1 to the power of p, x2 to the power of p, all the way down to xn to the power of p for our design matrix X, which obviously still is an n row by p plus 1 matrix. Now, this matrix actually has a special form because it's just powers of that particular vector. In particular, that vector to the power of 0, power 1, power 2, all the way down to the power of p. And this actually has a special name. This is called a Vandermonde matrix, which of course has some linear algebra theory associated behind it. Now, the first thing that I want to discuss in terms of some theoretical aspects about the Vandermonde matrix that you should know is the determinant, because we know that the determinant of a square matrix being equal to 0 implies that there is some dependence between the rows and or columns of that particular matrix. So this theorem is as follows. Let's assume that A is a Vandermonde matrix. And when I say a Vandermonde matrix, that means I have, for example, a column to the power of 0, a column to the power of 1, a column to the power of 2, all the way out to, for example, a column x to the power of n minus 1. Right, so let's assume that that is an m by n and hence has a determinant, at least the classically defined determinant. Then the determinant of this matrix A is going to be equal to the product as j ranges from 1 to m of xk minus xj. All right, and that should be j less than or equal to k less than or equal to n. All right, so that's the general representation of this determinant, but let's actually work through an example just to make sure we understand how it works. So let's take a baby 3 by 3 matrix. For example, let's consider the vector 3, 4, 5 raised to the power of 0, that's going to be 1, and raised to the power of 2, that's going to be 9, 16, and 25. Obviously, our values are going to be x1 is equal to 3, x2 is equal to 4, and x3 is equal to 5. So, via this relationship for the determinant of this Vandermonde matrix, you could either just find this via the classical expansion by submatrices. That would work perfectly fine. It's a small matrix. It shouldn't be too difficult. But this is going to be equal to, so we're going to do 4 minus 3, and then 5 minus 3, multiplied together, and then we're going to shift up to the next element, which is going to be 5 minus 4. So that's going to be equal to 1 times 2 times 1, which is going to be equal to 2. So that's going to be the determinant of this associated Vandermonde matrix. So when is this determinant equal to 0? So the determinant of a Vandermonde matrix is equal to 0 if and only if xj is equal to xk, because that's these differences, right? For at least one pair of indices jk, right? For example, if any of these numbers in this particular column repeat, then that entire row is going to be the same, and obviously that is a dependent row and or column, and hence the determinant will be equal to 0. Let's assume that you collect this small but sufficient bivariate dataset with 5 points. 0.1, 3.5 is the first point, 0.5, 4.8 as the second point, and so on. If you were to plot this graph, although a small set of points, on a Cartesian graph, you may assume that the dataset appears to be quadratically related, or possibly even cubically related, or what have you. So one could ask, okay, let's just try a bunch of models. For example, a simple linear, a simple quadratic, a simple cubic, and just see which one is best. So the first thing that we obviously would have to do is create a response vector y. So y is going to be equal to our responses, so 3.5, 4.8, 5.5, 6.1, and 3.7. Our predictor values, x is going to be equal to 0.1, 0.5, 0.7, 1.1, and 1.7. And obviously that's going to be defined as x1 for our first order linear term vector. And then obviously xk is going to be equal to each of those values, 0.1, 0.5, 0.7, 1.1, and 1.7, each raised to the power of k. And I'm actually just going to write that as x1 to the power of k, since we're just exponentiating each of those terms element-wise, right? And if you're working in the R programming language, defining that would work sufficiently. So once you have that and you can solve multiple linear regression models, now we can just try to fit a bunch of things together. So for example, let's assume we're interested in a first order linear model, in particular one of the form y is equal to beta 0 plus beta 1x plus epsilon. One can find that the predictor model y hat is going to be equal to approximately 4.01 plus 1.35 times x. So in terms of determining whether this model is appropriate or not, there's two common measures that some people usually resort to. The first is the p-value, because that's looking to see if we should reject whether or not the coefficient of beta 1 is close enough to 0 to imply that the model's not appropriate. So one can find that the p-value is approximately equal to 0.0993, which is relatively small, one could argue. And if you look at the r-squared adjusted value, you can find that's approximately equal to 5.335, which is not exactly close to 1, but some people may argue that it is. Right? But generally speaking, the p-value could be a lot smaller, and the r-squared value could be a lot larger. So generally speaking, one could say that these metrics are not so great. So if that is the case, maybe you would consider increasing the order of our model, for example, to a degree 2. So a degree 2 model would be equal to what? So that would be, for example, y is equal to beta 0 plus beta 1x plus beta 2x squared plus epsilon. And obviously these betas are not the same betas because they're corresponding to two different models. Now, before we start analyzing the model, you have to define how good is good in terms of the metrics for which you're aiming for, because one will find that as you increase the number of predictors, just like a multiple linear regression, the SSE will always converge to 0, right? In particular, we're going to have an overfitting issue, right? So for example, let's define our ideal values, for example, we can say that alpha is our 0.05, so once we get a p-value below that, then everything is wonderful. And let's assume that an ideal r squared adjusted value would be, let's say, 0.85, right? So let's assume we define these as good. So once we have one or both of these metrics satisfied, then we can say that that is the order model that we should reach. So if we fit this model via multiple linear regression, we can find that the predicted model y hat is going to be equal to approximately 2.98 plus 4.90x minus 1.93 x squared. And then we can get our model assessment parameters, in particular our p-value, one can find is approximately equal to 0.0073, and the associated r squared adjusted value is approximately 0.9853. Notice that both of our ideal criteria are met, therefore we should be very satisfied when we see that. Therefore, you should stop increasing the order and say that M2 appears to be a better fit for our model. But let's just actually go ahead and calculate what M3 will generate. So that's going to be our degree 3 model. One can actually find that the p-value is going to be approximately equal to 0.0654, and the r squared adjusted value is approximately 0.9894. Obviously, the r squared adjusted value does increase closer to 1. The p-value does not converge to 0 uniformly, but as you make the number of predictors go to infinity, eventually the p-value will be monotonically decreasing to 0, but I won't get into the proof of that, at least for right now, right? But you should not be surprised that the r squared value is decreasing or increasing every time we add a predictor, because that's one of the properties of the r squared and r squared adjusted metrics. So there's obviously two issues that we definitely need to be paying very close attention to. The first thing that we need to avoid, obviously, is overfitting. So overfitting is the sense when we're forcing our SSE to converge to 0 by increasing the number of predictors in our multiple linear regression model. But generally speaking, you should be able to prevent overfitting by implementing some sort of self-control by predefining your alpha value or predefining an ideal r squared adjusted value or some other metric that you have in front of you. The second issue that we have is what is referred to as structural multicollinearity. Some people just call it structure collinearity or just multicollinearity. And what that is when we introduce, for example, a predictor and that predictor raised to a power, obviously these two variables are dependent by design. And we already know that predictors on their own is a very bad thing, right? So we're introducing correlated random variables in our data, and that of course is going to lead to some very bad issues. For example, let's look at a couple metrics that we already should be familiar with analyzing in terms of dependence and multicollinearity from the multiple linear regression perspective. So let's assume that P corresponds to the number of predictors, which, at least for polynomial regression, is the order of our simple polynomial regression model. And let's consider 1, 2, and 3 for the same exact data set that we've actually been working with for the past couple of statements. So we've already calculated our models, 1, 2, and 3. Let's consider, for example, the condition number for the matrix X, which is just the quotient of the maximum and minimum singular values of that matrix. And let's also do the square root of the determinant of X transpose X, which can be viewed as the pseudo-determinant of the matrix X, since it's not technically square. So one can find that the condition number for our models 1, 2, and 3 is 3.31, 15.2, and a number approximately equal to 100. And the square root of the associated determinant of the XTX matrices for each of these models, one can find is 2.73, 1.69, and 0.37. As we can see that the condition number is getting larger, which is typically the case, and the determinant is getting smaller. So we already know that when the condition number gets larger, that means the precision and stability of our model is getting worse. And when the determinant is getting closer and closer to 0, that means the matrix in particular of XTX is getting closer and closer to a singular matrix, which means that the solution of our multiple linear regression equation, the beta hat is equal to XTX inverse XTY, is becoming more and more less reliable and eventually will not exist, since the inverse will not exist. So both of these are definitely a very bad thing. So how are we going to go about fixing these issues that we have by design created in our polynomial regression model? One common method that is often used to reduce the structural multicollinearity issues of polynomial regression models is what is known as variable standardization, which actually can be used for practically any regression model and will also be used in some later advanced statistical techniques such as principal component analysis. But what is variable standardization? So the root of the word standardization, in particular standardize, should sound familiar, and it definitely is going to be used here, and that's the standardization of variables. So what we're going to do is going to define what is called a standardized predictor, which is going to be represented by zk, which is going to be the original predictor minus the mean of that predictor divided by the standard deviation of that predictor. So here, these are all constants, and these are element-wise operations on this particular vector, xk. Therefore, once you standardize each of your predictors, x1, x2 down to xp, then you have what is called the standardized polynomial regression model. So the standardized polynomial regression model is going to be of the following form. Keep in mind we only have one predictor, therefore you should only be standardizing one vector. Therefore our standardized polynomial regression model is going to be equal to y is equal to beta 0 plus beta 1z, and then plus beta 2z squared. So that's just the squared value of the z standardized values. And that's going to continue all the way up to beta p z to the power of p plus epsilon. So that's our standardized regression model. Now let's look at the differences and similarities between the original model and the standardized regression model, just to see how we can interpret and see the pros and cons of this original model. So let's consider, for example, the quadratic model for the same data that we had before, which, keep in mind, we had the model, the quadratic model, approximately 2.98 plus 4.90x minus 1.92 minus 1.92x squared. And one can find that the condition number for that model, again, is approximately 15.2, and the p-value, actually let's do the square root of the determinant of xtx, that's approximately 1.69. The p-value for that model is approximately 0.0073, and the r-squared adjusted value is approximately 0.9853. And also, let's just mention one of the standard errors, in particular the standard error of beta 0, since that's usually the largest one. That's approximately equal to 0.15. Now, let's look at the same metrics, but for the standardized version of the quadratic model. Let's call that MZ2. So one can find that the coefficients of this model is going to be approximately equal to 5.70 plus 1.60z minus 0.72z squared. So for our metrics, one can find that the K matrix, or the condition number for X, or technically Z, is going to be approximately equal to 2.7. The square root of the determinant of xtx is going to be approximately equal to 7.45. The p-value, approximately 0.0073. And the associated r-squared adjusted value, approximately 0.9853. So to compare, notice the p-values and the r-squared adjusted values are the same exact thing, right? So therefore it has the same model predictions. And of course they have the same exact accuracy, right? But if you look at, for example, the condition number and the determinant, which used to be large and small respectively, now we have small and large condition and determinant respectively, right? So determinant's gotten farther from 0. Our condition numbers got closer to 1, right? So that means that the model has better precision and stability. Also, another advantage is that the coefficients for this model are all going to be in the same exact unit. In particular, they have no units, right? So that's a good advantage, especially if you're standardizing predictors for a general multiple linear regression model, not necessarily a polynomial one, right? So if you look at, for example, the standard error for the beta hat 0 term, for the standardized model, one can find that that is actually approximately equal to, let me see what that is. That's going to be approximately equal to 0.08. So notice that the standard error associated to 1 and usually all of your predictor coefficients are usually a lot smaller to work with, and that of course ties into the accuracy, precision, and also the stability and accuracy of your associated regression model. So in general, every time you're working with a polynomial regression model, you should always be standardizing your predictors to make your model a lot more precise and a lot more stable. The last thing I want to discuss today is how to build what is called a multiple polynomial regression model if you have more than one predictor and you want to use a polynomial regression model on each of those predictors. So let's assume, as an example, that we have 3 predictors. Let's call them x1, x2, and x3. And let's assume that we want to build a general quadratic polynomial regression model for these 3 predictors. What would that model look like? So let's assume that we have just one response variable, y, and we're obviously going to have our beta 0 intercept, but some people choose that to be 0, but I highly do not recommend allowing your beta 0 to be 0, even if you're standardizing your predictors for a variety of theoretical reasons. So then we're going to look at, for example, the linear terms for a model. So let's call them the following. Let's call it, for example, beta 1, 1, x1, plus beta 1, let's call it beta 1, 2 for the second, and then beta 1 for the third variable, x3. And then plus, then let's look at our quadratic terms. So beta 2 for our first variable, beta 2 for our second variable, and then beta 2 for our third variable, right? So what do we have here? So these are our linear terms, and then our quadratic terms. But that's not all the terms you can actually include in your polynomial regression model, because notice that we're not including any interaction terms. And you can, of course, include them. For example, you can include, for example, the interaction coefficient gamma 1, 2 with the variables x1, x2, and then gamma 1, 3, which is the interaction coefficient between variables 1 and 3 of x1 times x3. And then the interaction coefficient gamma 2, 3 between variables x2 and x3. So this is what we refer to as our first order. So our first order interaction terms, because it's one variable interacting with one other. And then the last term is that x1, x2, and x3 all interact with each other, which we can call, for example, gamma 1, 2, 3, which is x1, x2, and x3 multiplied together. Right? And that's all of our terms, and don't forget your residual term. And this is referred to as our second order interaction terms, or term in this case, right? So that's the interaction of one variable with two others. But generally speaking, some people do and do not include this term, especially if your goal is just build a general quadratic model, because x1, x2, x3 is a cubic term, not a quadratic term. Right, so how many predictors do we have here? So we have 3 on the first row, 3 for the second row, 3 for the third row, and 1 on the fourth row. So we have 3 plus 3 plus 3 plus 1. So the number of predictors that we have in this model, if you choose to include that lonely little cubic term at the end, is obviously going to be equal to 10. So obviously your n, which we already do know, should be bigger than p plus 1, which implies that n must be bigger than 11, which hopefully is not hard to do. But there is a lot of structural multicollinearity. So caution, there is a lot of structural multicollinearity. And why do I say a lot? Well, if you look at our terms, this term, this term, this term, and this term all are bad, right? And obviously I'm missing my exponents, 2, 2, and 2, so technically those are also multicollinearity issues, right? So out of our 10 terms, 7 of them have that multicollinearity issue, which is 70%, which is pretty big. Therefore, standardization of x1, x2, and x3 into z1, z2, z3 is a practical must. But those are all the fundamental things that you definitely need to know when you consider working with polynomial regression. Hope you enjoyed this video, and I'll see you in the next one. Take care.